It's quite common to see modern methods of construction used in low-rise buildings, but Ramboll have taken the same logic and we've applied it to tall buildings. And I'm going to take this opportunity to show you 4 buildings that we've worked on in the last 5 years. Who am I? My name is Gary Carpentier. I'm a technical director for Ramboll London Structures, and I'm also the precast lead for the UK. This is the Murano Residence project. It is designed by St James Homes. The designer was the architect Roger Stirk Harbour. The delivery architect was EPR. Ramboll were the structural engineers, and Expanded Langer Hall were the contractor. The building itself has a continuous floor plate up to 14 stories, and then the tower on the left continues up to 20 stories, and the central tower continues up to 28 stories. The building has a very unique external exoskeleton structure, and we designed this building as a precast concrete building, and that enabled us to build it in 63 weeks. The site is located between the Vauxhall Bridge and London Bridge. It's a very small site. It's only the size of 3 tennis courts, and it has a number of issues to deal with. On the right hand side you have the main line into London Waterloo, and on the left hand side you have the Albert Embankment, which is the main road into London, and we are only 20 metres from the River Thames itself. Okay. The building itself only has 12 external columns around the structure, and on either end of the building we have a steel frame exoskeleton, and where you would have a traditional core, we just have a spine wall that runs down the middle of the building. And located at the back of the building we have a lift shaft and walls around the stair core. The stability system for the building is quite unique in that it has a central spine wall running north-south across the building, providing stability. Obviously we needed to accommodate openings and be able to go through the wall area into the apartments. So the wall has a number of openings all the way down, and also as it gets into the basement it splits into 2 so that we can accommodate car park basement parking. On either end of the structure we have a exoskeleton frame which is formed of struts and ties, providing stability to the building in the east-west direction. And one of the key things about that was that those box sections themselves are 350 square box sections with a 25mm thick web, and we had to get those very early on at stage 2 because they were only actually available in China. Our challenge was to design the structure as a precast concrete structure. And to do that, what we did was we took the lattice slab system, also known as the filigree slab system, which has a 75mm biscuit at the base, and then you have in situ concrete topping. And then the planks themselves are then joined using stitch bars because you have a reduced stiffness across the joint. So we divided the slab up into elements, into concrete planks, and then they span onto in situ edge beams and columns. We incorporated in situ edge beams purely because the connection between the column and the beam would be very, very difficult to achieve in precast. The in situ edge beams at either end of the building also enable us to construct the building without the need for the exoskeleton frame. And centrally where we have the spine walls, they were changed to twin wall construction, which is very, very similar to lattice slab in that you have the biscuit on either side, and then the central core of the wall is filled with concrete on site. At the rear of the building we have the lift shaft and stair core area, and these were done as black concrete walls, precast, and were also a main feature of the structure. The steel frame is connected to the floor at every 7 floors via a steel node, and the node allows the central column to be released vertically every 7 floors. The load that comes through the node is then spread equally down through diagonal struts, down into the precast columns, and obviously then down into the foundations. And it also acts as the connection to the tension rods that are used to stabilise the building. We produce a fully unitised Revit model for all the precast structures that we do, and each one of those models, every element contains all the metadata for the reinforcement, any builder's work or any other requirements. And that is then taken as a model straight to the factory, and from the factory's software is then taken straight into manufacture. And I think you can see there from the diagram showing the column bars, the complexity of actually modelling one of these precast columns. A full construction stage analysis was carried out on the buildings, and it was evident that the building would see small twists in the structure if the tendons weren't stressed equally. And I just add that the diagram we show there is obviously exaggerated. The twists aren't quite as much as you see there. A further challenge was that our contractor needed to put the crane on level 14, and you can see that in the photograph on the right hand side. And this was because we couldn't oversail the structure if we were to go up to 28 stories. Sorry, we couldn't oversail the railway if we went up to 28 stories. So we had to put that tower crane on top of 14 stories of structure. And to deal with the issue, what we did was we post-tensioned the top of the columns. We cast in macalloy bars into the precast that enabled us to deal with the tension forces that we would see from that tower crane. The analysis allowed us to build the structure so that we could always build the structure up to a point which was one floor above the critical node, whilst maintaining the verticality of our structure. Riverlight is a St James development, and the design team was actually the same team that we had for Murano. Rochester Harbour were the designers, EPR were the delivery architect, Ramboll again the structural engineers, and Expanded Langerolt with the contractor. Riverlight is actually located a little bit further south of Murano and is located in the Nine Elms area. The site is adjacent to the River Thames, and the site itself is approximately 30,000 square metres. The project consisted of 6 separate buildings across the site, with the tallest buildings being on the east side of the site, and they are up to 20 stories in height. The 6 buildings are then linked at basement level by a 20,000 square metre 2-storey basement, which is also alongside the river itself. The buildings are all 15 metres wide, and they vary in length between 40 to 100 metres and have one or more cores located around the external facade. Through the building we have a number of apartment walls, and all the walls are designed as 220 millimetre thick in situ concrete or precast as we got higher up the structure, so that they would fit within the apartment and maximise the area. At the ends of the building we have external steel ties, and they're used to support the edges of the floor slabs in the permanent condition. And then equally we have downstand beams that were used to enable early removal of props during construction. The steel nodes that you see on the outside of the building are cast into the concrete floor slabs at each level, and they allow obviously the external steelwork frame bracing members to be connected to the concrete structure. One of the defining features of all the Riverlight buildings is that they have a 9.3 metre long cantilever prow structure, and these are prows which are 220 millimetre thick shear walls which support the loads from the columns above. As you can see, the cantilever walls themselves have tie forces at levels 5 and 6, and these are also then balanced out by compression forces which go through level 1 and 2. And these are taken by a heavily reinforced strip right the way through the centre of the building from both ends. At every other floor around the external facade of the building there is a feature beam that is present, and the architect wanted this to be a high quality precast finish. So this left us with a challenge of how do we incorporate the node and the beam together. So we ended up with a steel node which was then placed on top of the shuttering, and we left a slot in the back of the precast beam, and it enabled us then to be able to push the node into the back of the slot, and then there's a shadow gap between the steel, so the whole thing is then tied into the structure. whilst most of the floor slabs were either in situ or post-tension, depending on the structure, we did actually take the opportunity to use precast construction for all of the cores and the columns on most of the buildings in the higher levels of the structures. So this project is 250 City Road. It was a project by the developer Berkeley Homes. The architect this time was Foster's Architecture, and the building itself is located in the London Borough of Islington. The original designer on this one was CH2M Hill, and Ramboll became involved because we were appointed by Expanded Limited and asked if we could take the existing in situ structure and change it into a precast concrete structure. The development itself consisted of the Phase 1 Northwest Tower and also some of the surrounding 8 to 15 storey buildings that were on the site. The floor plate is approximately 38 metres long and about 22 metres wide. The slab thickness is 250 millimetres thick, and equally around the perimeter you have a number of columns which are either 6 or 7 metres apart. The building has a 10 metre by 7 metre central core which is continuous for the full height of the building, and that varies in thickness from 600 millimetres at the base up to sort of 325 millimetres near the top. And then at the lower section of the building we have the outrigger walls that you see in red on the left hand side, and they were generally made at a thickness so that they fit between the apartments. So the stability system of the tower itself has a outrigger walls between levels 8 and level 27, and then from level 27 up to level 42 we then have a moment frame structure, and equally at the base of the building we have cores and outrigger columns and wall slab arrangement. So we have quite a number of buildings on the site that we're going to be precast. So because of that, we decided not to actually cast the core itself as a precast core. So the core is actually an in situ core, but we did then look at the opportunity of where we could use twin walls for the outrigger walls. So most of the outrigger walls are twin wall structures. So our challenge was to take the existing in situ concrete structure and then convert that obviously into a precast structure. And we took a very similar approach to what we saw on Murano earlier. We used the filigree slab type approach. So this is one of the actual smaller buildings. This is block 9, which was the 15-storey structure. And what we did here was we took the column strip method. So we have the primary planks over the column strips, and then the smaller secondary planks spanning onto the primary planks. And we looked to maximise our product base on this, so where we can, the planks are exactly the same size to maximise manufacturing. So for the tower itself, the spacing of the column dictates the fact that you can't use just secondary planks. So when I say secondary and primary, I mean the primary has the main reinforcement in it. So we ended up using primary planks for all of these, spanning from the central core to the outside columns. So again, the principle was the same. We split the floor slab up into a number of planks and tried to get repetition in those planks throughout the structure. And that actually then culminated us in achieving a building which had 1,234 precast planks. And that enabled us then to do a sort of 2 to 3 day floor cycle, which was very quick for the tower. And with the tower being 42 stories high, I think we actually finished this in about 2 or 3 weeks. So the Wood Walford development is a mixed-use development. It's being constructed in multiple phases between 2015 to 2025. And the development incorporates approximately 30 buildings, and they range in various heights from low-rise to high-rise. So the Wood Wharf site is actually located at the Isle of Dogs in the borough of Tower Hamlets, and it is opposite the O2. And our high-rise team at Ramboll, we've designed the 16-storey block A2 and also the 46-storey building A3. And again, on this one, the client was Canary Wharf Group, and The designer was Stanton Williams. The buildings that Ramboll designed were the building A2 and A3, and you can see there on the right hand side that the actual buildings themselves stand on a pile marine deck. So building A2 was a traditional in situ concrete structure with a central core, so brace frame structure, and it's a fully in situ frame. The 46-storey tower itself is a traditional braced in situ concrete structure, and we did actually look at this structure to see whether we could do it in precast, but it was decided that due to the irregularity of the grid, it didn't really suit precast or PT, so in situ was the way to go forward. We did actually want to challenge the structure and look at whether we could use modern methods. So to increase the speed of construction, it was decided that we would actually try and design the columns as precast columns. They were cast on site. The columns themselves are 2 stories in height, and obviously there was then the issue that we needed to consider the connection between the slab itself and the column junction being a 2-story column. And you can see there in the picture that when you try to do this, and we do this quite regularly on our structures, that you need to provide additional bracing within the reinforcement in the unreinforced concrete element. So to summarise, I think you'll agree that those projects demonstrate that you are able to build tall buildings using modern methods of construction, and it also takes the combined benefits of using in situ precast and concrete construction.